Hello and welcome to the next stop on our tour of pathfinding. So last time we got our path data up and running as far as a one-to-one mapping. So that's what we got going, a one-to-one mapping, and we'd confirmed that we had locations, things like that coming through correctly. We got some basic debug stuff going, and we made sure our file sizes were much more manageable. So we've got a good ground point. What we're going to focus on now is polishing up that base a bit and getting it so that it is as robust and reliable as it possibly can be for them being able to build the pathfinding on top of that. So key focus there is going to be supporting multiple resolutions of data, improving some of the debug, things like that. So let's just dive on in. So we've still got our previous setup where we can show our nodes, and we've got that registration happening nicely. So all of that's working quite well. So first thing I want to start doing is changing things with that path data sets, the view there. And easiest way to actually improve that, because with switching things to being a scriptable object, I don't really need customization for the drawing for that. So I'm actually going to just get rid of the property draw script for it because that saves me having to specifically set stuff up. So it's linking to the asset, which is good. I can see the size, everything like that, which is great. So starting point is I want to get this working with different resolutions because we can see what it looks like at the 1 meter resolution. Well, it's going to be smaller than 1 meter. We want to switch this to those coarser resolutions. So I'm going to immediately change this to 2 by 2, and then we're going to get this up and running. So there's going to be a few areas that we need to change. And starting point here is we're going to need to make some changes to the size calculations that we're doing here, because this resolution is actually going to be different. Because depending upon the size that we've set, that will actually be less. So the easiest thing we can do there is that height map resolution, we actually divide this by our resolution information from our config. So divided by path data set dot resolution, which we can cast that to an integer. So that's why this intentionally, if we take a look, uses these are set to 1, 2, 4, 8, 16. It means we can very easily just do a divide there. So that's good. That works for getting the resolution. Now the height map scale, that's actually going to change as well. The size of our individual nodes is going to be different. And so with this, we actually need to start thinking about, okay, how is this going to divide? Because if we look at our terrain and we look at the scaling, so our height map is 1025 by 1025. That's because the way the height map works is we've got the height of individual vertices. And while that height map has that number of vertices, we actually, each grid tile is bounded by 4 vertices there. So if we did 1025 divided by this, then that would mean our size, it's not really going to be that accurate. So what we're going to do is actually a bit of a change so that each height map pixel is going to correspond to a vertex at the edge of our grid. Because how this would currently look is, and we've conveniently got a few of these placed objects on it, our grid cells pretty much line up with this cube. So we're going to actually change that so that it is going to be more like this, where our grid cells are bound by actually those height map points. That's going to mean we need to do a few more calculations for working out stuff like the height. It's also going to mean our size changes a little bit here. Path data size here it's actually going to be, because the height map resolutions, those are always going to be an odd number. And if we take a look at the options we have for those, we'll see they're all odd numbers, and they're all odd numbers that are a power of 2. So we're going to subtract 1 from that. That's why I went for power of 2 for these resolution options here. So height map resolution is actually going to be -1. Now that's going to change our height map scale, because we have each cell stores more data. So this is actually going to need to be modified, where we have to do height map scale.x multiplied by our resolution, and height map scale.z, and we do the exact same thing. Obviously don't do y, it's only the horizontal planes that we do. So what we're doing is determine the path data size, allowing for scale. Determine the scaled node size. So I'm going to actually rename this to node size. So that's good. And these, because these are useful information that I'm needing, I'm going to actually pass these down into our next function as well. And node size. So that's all the changes I need to make at this point. But then down here, I'm going to have, I'll actually do the renaming of some of this stuff first. So we'll have int path data size. So let's just get rid of this. We will also change this to node size, and then pass that directly in. Vector 3 node size. So that's good. So we can retrieve the heights. Now this is one where we actually need to make a slight change here, because we still need to retrieve the entire height map. That's a slight change we have to make there. And one of the things we're going to have to handle is this changing between coordinates. And that's okay, we'll be able to do that. So, okay. Here we are, build the nodes. Now this will be the main area that changes, and this will be the area that's a little bit of a challenge in terms of what we need to do, because there's a few sort of clever things we need to be doing with this. But we'll largely be able to have it contained within this. The building up of the neighbors, nothing changes for that. So that's the good news. But if we look at the data we need to get out, so we have things that are at different resolutions. And even if we switch back to 1 by 1, things are already at a different resolution. So we've got height information that's at 1 resolution. Slope information is at the same resolution as that, but our path data is at a different resolution. So we need to look at how we can scale and combine that. So what I'm going to do is I'm going to set up a function here. I'm going to call sample height map, that it expects to be given our height map, which is a 2D array. So expects that height map, and it's going to expect to know the height map resolution. I could retrieve it from directly the height map. Actually, I will, just to save having to do that extra work there. So we're sampling it. We need to know the scale. So E resolution, and then we need to know the location we're sampling. So int row, int column. And what this is going to replace is where we were doing this calculation. It's going to replace that. So we're going to have float height, and we'll say sample height map. We provide it the height map. We provide it resolution, and then we provide it with the row and the column, and we'll use it directly here. And that can be the scaled height. So we can still have to run it through. The scaling is completely fine. But it's going to do that. So retrieve the height. So that's good. We need to do a similar thing with the slope. So I'm going to also have float sample slope map. This uses, we don't need to pass in the slope map because we've already got that, but we do need to pass in the resolution and column. So this is a bit of a change from what we were doing here with providing the texture U and V. That's because that filtering, we're not going to be able to do it exactly the same as we could before. But there might be a couple little tricks that we can do with this. I am going to just, for now, comment these out. And then we will have our helper function. So float cos slope is equal to sample slope map. And again, configuration, resolution, row, column. So what I'm intentionally doing here is wrapping the logic so that I'm not having to do the same sort of stuff, in multiple different places. I'm trying to make it that the logic is as combined and merged as possible, just so it's centralized in one particular spot. So now we need to work out, okay, we need to sample this height map. So our row and column are going to be within the scale of the path data, whereas our height map is going to be using its own sort of scaling. So we need to do a bit of a coordinate conversion there. And what we're going to do is we're going to sample a section of the height map, and we are going to get the average height and return that. So we're going to end up with height sum, and then we'll have int num samples, and we'll return, well, if num samples is equal to 0, we just return 0. Otherwise, we return height sum divided by num samples. So, okay, that works. Now we need to be able to work out where in the height map we sample and how large a range we check. So the range that we check, if we have a resolution of 1, we're going to need to sample a 2 by 2 area. If we have a resolution of 2, then we need to sample an area that is 3 by 3. So it's going to always be 1 plus our resolution number. So int, and we could call this the range. It's going to be convert our resolution to an integer plus 1. Then we need to work out our starting row and column. So our starting, and we'll loop over those. So for int working row, it's going to be whatever our row value is multiplied by our resolution. And we'll actually what we'll do is we'll do 0. Working row is less than range. Update that. Then we do the same thing with the columns. So working column, 0. Working col is less than range, plus plus working col. Now we need to check and see if these are actually even a valid location to sample. Because, okay, well, if working row is greater than or equal to height map dot get length, I'm going to store this in a separate variable. And get length, you tell it which dimension you want to get the length of. It's not going to matter for this because we know the height map is square. Height map size. It's likely not going to be a slow operation. If it does show up as being slow, we absolutely could optimize it. But if the row is greater than that, we do nothing. So out of range, do nothing. In this case, same thing for the working column. If working col is greater than or equal to height map size, continue. Now we need to offset by our actual starting location here. So what we could do is our starting row, we can store that because starting row and column are always going to be the same. So starting row is equal to row times by our resolution. Same with the column, starting col is column times by our resolution. Read the key height map parameters. Sum of the height values. So this would end up being working row, and what we could say here is working row is equal to starting row. Then our range, starting row plus that, and we can actually simplify that, and we add in an additional check here, and working row is less than height map size. Means our for loop here is getting a little bit more complicated. These are a valid thing to do. We can check multiple conditions here though. That's completely fine. Our working column starts as being starting col, which is good. And we do the same thing here. Starting col plus range. And working col is less than height map size, which means we also don't need to do that check. Because then we can just say, well, height sum plus equals, and we sample from a height map, and if we remember how we were sampling from that, we would be doing height map and working col, working row, plus plus null samples. Now for now, I'm just going to say that the slope map, we just always return 1. Because I want to check that this height map 1 is working, because we've made some pretty significant changes here for this, and it's really, really important to make sure that these changes are actually working to start with. So first thing I'm going to do is just actually rebuild the path data with this change and see if it's looking correct. And in particular, see if it's looking correct at the different resolutions. So generate. Now it's run. Now we can see that is broadly looking correct. Particularly in flat areas, it's looking pretty good. Steep areas, though, we notice it doesn't. Steep areas, it definitely is a little bit off. Now we want to check back at 1 by 1 and see how that works. 1 by 1 should have less areas where it's off, and it does. It still does have cases where it is off. And so that's something where we want to look at improving that definitely. So it's broadly working, which is good. And if we go for even coarser, you can see that's, again, still broadly working, but we do get areas where it is quite distorted. And this is something where, practically, we wouldn't then use something that's an 8 by 8 or 16 by 16 size for this. We'd look and see what's a reasonable sort of size. You don't want too much vertical variation in your actual path data. And I would actually say 2 by 2 is broadly where I would be looking at for this, and it's generally pretty close to on the mark. What we could also do is, so we're doing an approach here of we are sampling the height map, and we want to check and see, you know, edges is an area where things could go wrong, and we want to make sure those are looking correct, which they're, again, broadly speaking, looking pretty reasonable. But we do get those distortions happening, so we want to be able to improve upon that, which we can, because we've got this gathering that data, but it definitely doesn't work super well in steep slopes, and we can see those are appearing a bit under that, which is to be expected. So we can improve that though. We know that it's definitely registering and conforming to the particular bits of terrain. So we know we haven't gotten anything flipped, which is great, but we do need to improve how accurate this is. So there's a couple of ways that we've got for doing that. One of the options is we can actually, with the terrain, so so our source terrain, if we look at our height options, we have the ability to say, okay, give me the interpolated height. And the way this works is you give it a normalized X and Y location. So we can check and see how that works and how close that is to sort of what we're after. So how we would go about doing that is we would need to, we've got our starting row and column. And if we check and compare that, and so float interpolated height, so we'll see if this works as a better version of it. So we'll return the interpolated height. So we need a 0 to 1 value for these. We know our starting row and column. So we could actually do starting row plus resolution divided by 2. So halfway through the resolution. I'm going to actually convert the resolution to a float. So that divided by our height map size. That's going to be our Y value. And then our X value is going to be similar sort of thing, but we use column. And so with this, provide it with X and Y. So we'll see how these look in terms of value, whether this should match a lot better. But this is something where we'll get a good sense with this of whether it does or not. So we've generated the path data. Now that you can see we're not getting actually any values appearing for this. And it's worth us looking under, and we don't see anything. So this would be something where what we want to do is check and see what we're getting here for values, just to make sure it's correctly doing the calculations. So, because we should have X and Y values there, it should be between 0 and 1. So if we run and generate our data again, can see what values we're getting. And we're wanting to particularly pay attention to what we get for the X and Y values there are going to be key. So X is 0, Y is 0. If we take a look at height map size, that seems about right. Our starting column, and then it's adding our resolution. So that looks about right. If we come back and check this at a few key points, and so we can see what the issue is there. That's actually giving us out the scaled height. So that's something where if we were using that interpolated height, we would not do that calculation. So let's just test it with that and see if that gives us something that's a little bit more accurate. So that by the looks of it, we've probably got our values here swapped in terms of the row and column. Very easy to have happen in terms of the different coordinate systems that get used there. So we'll test again with that. This is why the importance of these debug displays. So we can see that generally conforms a little better, but it's still, we get those areas where on steep slopes, it is going to be a little bit off. It's generally, broadly speaking, I would say better. So it has worked a lot better, but we do get cases where it is a little bit off still. And what that might be is what it's actually using as its sample point there. And what I suspect is when we're setting the central location here, because we've sort of changed this so that the center point is actually a little bit offset. So we would need to change how we're calculating our world position here. And this would actually be rho plus 0.5. So we're centering it. So plus 0.5. So this means the position that we have for a node is actually its dead center, which is going to work a lot better. We need to do the adjustment here as well, because otherwise these will be off too. Plus 0.5. So with that, we'll regenerate and take a look, but that should have them conforming a little bit better in the steeper slopes. And we can see that is definitely a bit better for lining up with the slopes. That's significantly better. So that's using the interpolated height. We can try back with what we previously had with doing the sampling, because I would prefer to do the sampling if possible. Map scale, sorry, cell size, node size, dot y, and if we switch this back to being the sampling based method, it's probably going to be pretty close to the interpolated one then. We'll regenerate and check. And yeah, with those changes, it's pretty much spot on now. So that is looking pretty good. So I'll keep it with the value that it's using there. So, okay, we know we've got our height data, and I'll check it at the other resolutions as well. So 1 by 1 will be a lot more data, but really close. With those other changes, let's go for 4 by 4. Looking pretty good. So those changes have meant we get much better conforming to the terrain. Still going to get, if we go for too large a node size, we'll still get issues. That's to be expected. If you've got a lot of variation in your features, that's going to happen. But 4 by 4 is looking pretty good. And one of the things we'll notice is the big difference this makes in the size of our path data asset. It was 20 meg. At 4 by 4, it goes down to 1. So huge difference. And that's because at 4 by 4, it's not that we've got a quarter of the data, we've got a 16th of the data. So it's a massive reduction. But we don't have slope stuff factored in yet. So we need to get that back up and running. So we're going to do that. And we can do a fairly similar approach for this. So it's going to look quite similar. Going to actually start off initially with the exact same approach. But I'm going to rename these. So slope sum. So our size. Well, we have our source slope map, and we have width, and we have height. So we have the key bits of information we need. So we can be checking this with source slope map height, source slope map width. Don't need those. The parameters, some slope values, and then we can say, okay, well, source slope map, and we need to get pixel, working col, working row, and that should do the trick because we just grab out then the red value. That gives us back the sum of that. Now, good chance we might need to swap some of the values. If we do, that's fine. But let's check if this is now working correctly. So we'll generate that data, and that's looking pretty good. Those slopes are working. It'll be most clear if we go for like a 2 by 2. Can see, yep, steep areas there are working. Now it is potentially going to miss some, and that's because we are averaging it. What I would potentially look at doing is our slope map. We actually, rather than taking the sum here, we take the maximum. Actually, sorry, to be the minimum. Minimum is going to correspond towards the steepest value. So I'm going to change this to the min slope, which would start at 1, corresponding to being completely flat. And then what I will do is, even though we're calling it min slope, a lower value actually means steeper, but that's okay. So min slope, mathf, min slope, and the value we retrieve here. This is just one of the things you need to watch for when you're working with stuff where you're effectively downsampling the data, where average works okay for some things, like height. Average is great. But for when we're dealing with information like slope that determines passability of an area, it's a little bit risky to be using it. We often need to use some smarter methods. So we regenerate, and we'll notice we've got a lot more ones that are showing up as red. We are still missing some patches here, and I suspect one thing we can do is we convert back over to 1 by 1 as our double check. You can see these patches are not fully lining up, and so that makes me suspicious that we have swapped, need to swap the values here. Again, debug displays, so important because without them, it's very, very easy to miss things like this. And that's looking better. That is looking spot on for what we would expect to see. If we go back to 4 by 4, again, still good. So we could try having this back as the average. So I'm going to switch it back to doing the average, but with the row and column swap, because we obviously had them wrong, but it wasn't really showing up super well. But we'll try and see if average works okay. My inclination is I would still probably go for using the min, just because these are gameplay affecting, and there is a chance, fairly high chance, of some nasty artifacts of if we had a steep slope, this area where you got steep slope and a flat area, and it could distort things, but it actually looks all right. I think it'll actually be okay. It seems to be, yeah, that's one where I would have expected that to have gotten picked up. So there's a few ones where I do think the min approach is going to work better. So I will change this to using min slope. I think that's going to be a safer course because I think otherwise we just run the risk of having it just give us the areas where it's like, yeah, no, this is possible. It's like, it's not really. So I think we'll keep this as using min slope. I think is going to be a lot safer. So height averaging works good. Yeah, so that changed to red. I think that's better. And we can see these ones around the base here. I think, yeah, using the min slope, I'm happier with those results. The data there looks a lot cleaner, a lot better for what I would be expecting. So that looks good. Happy with that. So we're going to, as a final sort of thing for this, improve the debug displays a little bit. So these debug displays are okay, but I want to make them better. I want to, with the node connections, I want to make it a bit more explicit where it's actually, we see the connection drawn there. Draw the nodes and draw the edges. So I'm going to, again, into the node, set up a few improvements here of being able to check what neighbors it has. So public bool has neighbor, and I'm going to start abbreviating these to make it a little bit cleaner. So neighbor flags has flag, neighbor flags north. So we'll just set up these. This will make it a lot cleaner for working with. And then what we'll do is I want to make it that these, again, we want to make sure we've got solid data. So I'm going to change these so that rather than just drawing roughly in the direction, that they actually draw a direct link to the neighbor so that we can see definitively what it's connected to, and just make sure that we've got those connections correct and that we're also able to retrieve things like the specific neighbor. I think will be really important. So then this is able to become as neighbor north. So it cleans these up a lot. I strongly recommend making use of properties for things like of this. It simplifies how your code looks, which that in turn means that if your code's simpler, it's easier to grasp everything that's happening with it, and it means you're able to avoid potential problems. And when we're working with something like path data, where our code gets quite complex and there's a lot of things building on top of other things, it's really important to try and have it be as simple, comprehensible as it possibly can be. So if it has that neighbor, I want to have a handy way of being able to just say, okay, get a particular neighbor. So I think the path data is the best thing to go through for that. So I'm going to make it that this draw debug is given the path data as well. And we'll say that that has path data. And we know we've got that neighbor. So what we can actually do is we can go, okay, well, path data. And actually, I'll rename that to path data just to make it cleaner. So we already know we can retrieve a node. So we can do get node, node location, also node grid pos plus grid helpers step north dot world pos. So we can just easily do that. That means that this will draw a direct connection to that particular node. So it just means that we know reliably where those connections are. And that's really important because this is data that we need this data to work for any of the pathfinding stuff to actually be valid. So it's very critical to get this up and running. You absolutely could save time by not setting up debug stuff. I really would recommend don't do that. You will end up needing the debug stuff, and you're better to have it early where you can verify any potential problems to begin with, and then sort those out at that particular point. So that looks good. So what I might do is offset these so they link down, so we'll actually be able to tell that we've got cross links and things like that because they'll be coming from different heights. So that looks good. So let's turn on our edge debugging and make sure that that is working correctly. So that looks good, and we can see our connections, and in particular we can see the direct connections are happening there between the particular nodes. That's looking really good. Water is connecting to water, land is connecting to land. We have our sections here being linked up. That is looking excellent. I'm very, very happy with how that's looking. Cool. So we know that side's working. Great. Well, our path data, we could have multiple sets of it. We haven't tested that it works when we have multiple sets built. So we're going to need to do that. It's also going to mean we need to make a change to our debug display setup because these are going to go into the actual path data set because they kind of need to be per path data set. They have to be tied to that, unfortunately. Otherwise, it doesn't really make sort of a lot of useful sense, which means I'm going to change this to pass in the path data set. And we will check its debug setting. And that will also then be changed to make those public, because we don't need to keep those as protected. They're debug ones, and we'll be able to retrieve the path data here. Path data set dot data. So that just means the debug controls are within each particular individual one, which is good. So I want to check that this still works, which it does, which is good. So I'm going to add in another set. So I'm going to say I want one set that's 1 by 1, one set that's 4 by 4. I'm going to clear out that data because otherwise it would be referring to the same set of data, which would be bad. That looks pretty good. Let's build it. Take it a little bit of time because we're obviously building two sets of data. And if we take a look at our scene, we've got two sets of data, which is good. Let's turn on the debug for our 1 by 1. Looks correct. Turn it on for the other one. Again, correct. And so we've got two separate sets of data, which is good. So, okay, multiple data sets is working, which is excellent. Let's add in a final thing here in terms of public bool can use water. Because what we will do is, well, we'll add in our configuration here. We've already got the path data config coming through. And again, this is one where I will change this to be using the actual configuration as well. So we will pass that in. Configuration, path data set, configuration. So if that's the case, R2, F configuration dot can use water, and now we check for slightly different setup. We're looking for either neighbor is walkable and node is water. So the current node is water. And either the neighbor is walkable and our current node is water, or the neighbor is water and we are walkable. Then in that case, we can mark it as being both walkable and also water. And so we can add in the actual flags there. So actually we don't need to mark it as walkable, but we can add in that connection there. If we connect to water, then allow those connections. We can. So it can still only bridge water and walkable, but this should allow it that what we might do is for our 4-meter resolution one, we'll enable that as a thing there. So our 4-meter one, we'll say can use water. Going to generate the path data. And then what we are particularly looking for is, let's look first at the edges for 1 by 1. So edges for 1 by 1, we do have our gaps as expected around the water. So we've got these boundaries where it's not connecting, which is good. So we'll turn that off. Now let's look for this. We can see it's bridging connections. So we've got our path data, so we can have different qualities, different attributes and aspects there to it, which is really, really handy. So this is good so far. We've got path data working with different resolutions. We've got better display of our edges. We've still kept the data size really manageable. We can see our file sizes there are quite good. There's one final thing that I want to do with this, and that is building up a set of unique areas. So giving each node an area ID. And the reason for this is it's really valuable to have that information because area IDs allow us to mark out contiguous blocks, because that means that if we've got an AI that needs to pathfind between two locations, we can just check the ID quickly and see, well, there's no connection here. I'm not going to try and find a path. So it allows us to eliminate doing a whole bunch of work for those cases. So it's a really valuable thing to optimize. Also means if the AI is wanting to search for stuff just in a certain range, we can do that. So we're going to get that set up as a initial thing. So what that's going to mean is our node is going to have public int area ID. And that means that's also still not going to be serialized, which is fine. So serialized field int area IDs. We again do similar logic with that for converting down here. So node index, area ID. Actually, not in the initialized node, goes in our deserialize. So nodes, index, area ID. And then we need to manage the storage of that as well. So new int and then we just transfer that data over. Excellent. So that's just going to make it really easy for us having this data there. What I am going to do is, because it will be grumpy with trying to process that data, which is fine, I'm going to unlink those and it will be able to regenerate them, which is cool. we need to build those area IDs. So that's the thing that we will do after we generate the path data here, is build area IDs. And I'm going to give it the path data. And I want to do this in a separate function. Find build area IDs. Okay, so with building up the areas, this is actually a really challenging thing. And it seems like it shouldn't be, but it actually is, in terms of this really exposes the large amount of data we're having to process. So we need to do something where we're avoiding memory allocations as much as possible, and where if we are allocating stuff or checking things, we're able to do that super, super efficiently. So one of the things that I'm going to do is I need to potentially process, well, not potentially, I do need to process every node. So I'm going to keep track of what nodes I've actually visited. So I'm going to have a visited list. So this will be an array visited nodes, or node visited, nodes visited. That's going to be a new rule. We can do path data dot dimensions dot x times path data dimensions dot y, and I've actually modified these back to being public just to make it easy to work with. So, okay, we're keeping track of what ones are visited, and then we need to work out, okay, well, which ones do we then potentially process? So we're going to go through initially just all of them. We need to keep track of the current area ID. Area ID is equal to 1. So then for int index is equal to 0, index is less than path data nodes length. So first thing I do is check if this node is visited. Skip if already visited. So if nodes visited index, then do nothing. So that's good. The other thing I can do is, and actually I can avoid a memory allocation there because I can just work with the area ID. So if the actual node, if its area ID is greater than or equal to 0, it's already set. Because what I'm doing over in the path data here is I'm initializing the area ID to -1. So if it's already visited, I do nothing. Then, okay, I want to build that area. So build area. So I need to give it that node. It's going to need the path data because it's working with that. It's going to need that area ID as well. But now knows, okay, here's a starting point, build out from there. So build area, and this has, actually this will be flood fill area. There's a better name for it. Oops, that renamed the wrong thing. So flood fill area, path data node, seed node, path data, and the area ID. So first thing this is going to do is set the area ID of that seed node. Area ID is equal to our area ID. So what I will do here is after we've flood filled an area, we increment that. Also going to do a little bit of a check here. So if this has no neighbors, I don't even want to build an area ID for it. So if this neighbor flags is equal to none, then I skip it. It doesn't have an area ID. Oh, actually, I'll give it an area ID, but of 0. So path data nodes, index, area ID is equal to 0, which will treat 0 as unconnected areas. Node has no connections. Mark as isolated. So we're only building ones for things that we know they have neighbors, that there will actually be other connected nodes. So that's good. So we've set the seed node's area ID. So tag the node. Now we might not need to tag it immediately, but we'll go with this. So I need to process being able to keep track of these. I need a working list of things to run through. So this is where using a queue can be really handy. So I'm going to use a queue, and I don't want it to be a queue of my nodes. I want to actually use a queue of the locations. So nodes to process. So that's a new queue. Queue is going to be a little bit faster for the kind of stuff we're doing with this. So nodes to process in queue, the seed node. And then while nodes to process count is greater than 0, and what we enqueue is actually seed node grid position. So while we have things to process, so first thing we do is we dequeue that location. So nodes to process dot dequeue, that gives us our location there, which we can go, okay, well, node is equal to path data, get node at that location. We tag it. So we retrieve it, we tag it. Nice advantage with dequeue is we retrieve it and also remove it at the same point in time. Now we need to add in the neighbors. Add in any neighbors. And we only want to add in a neighbor if it hasn't already actually been processed. But that's something where node has neighbor to the north. Then we're going to need to retrieve that. So we can say, okay, well, path data, get node, our node, grid pos plus grid helpers, and our north step. So neighbor, which we know that's going to be valid, because it has to be. But we can then check and see if that actually has an area ID already. So if neighbor area ID is, so we only want to add it if this is less than 0. If it is, then nodes to process, enqueue, neighbor.gridpos. So we only enqueue it if it hasn't actually already been processed. So that looks good. And we'll be able to do a similar process there for all of the ones. But the catch with this is we could enqueue something multiple times. Is very, very possible. So this is something where we need to know if we have already enqueued a thing to work. Because if we have, we don't want to actually process it. We don't want to potentially process it again. If it's already been added into the queue, really, really don't want to add it again. So what I would look at doing for something like this is we could actually use a specific area ID as this is about to be set as a criteria for not putting it in there. Would be one option there. We could also bring back having that bool list of, okay, we've flagged for processing. So that could be a useful thing. So we might bring that back, our bool array here. So flagged for processing, new bool, path data dimensions X, dimensions Y. This allows us to make sure we're not doing extra processing if we don't have to. So what we would do is as soon as we have processed something, we're going to flag it. So if we go to add it, we're going to need to check its index. So var neighbor index is going to be node gridpos X plus node gridpos Y times by path data's dimensions dot X. So F flagged for processing neighbor index, continue, and we'll pass that in as a helper here, bool, flagged for processing, just so that we're not duplicating that every time, because I want to, again, minimize memory allocations. So if it's already flagged for processing, flagged, then ignore. If already processed, then ignore. And otherwise, what we'll do is flagged for processing, neighbor index is equal to true. So that'll stop us accidentally flagging it multiple times. The other thing we could also do here is it is possible that we potentially still could add in something multiple times. I don't think it's likely, but as a safety check, if node area ID is greater than or equal to 0, skip it. It's already been looked at. We're not going to do anything with that again. So this logic here, we're going to need to do this a whole bunch of times. So I'd actually move this into its own little helper function. So this would be evaluate, or actually it's flood fill area helper, one of a better name for it. Now it needs a lot of this information. It needs our path data and the flagged for processing. So it's going to need those. It needs to know the current node that we're working with. So path data node, current node. So that's going to come down here. Continues, change to a return. And it also needs this nodes to process because it actually has to enqueue into that. So we'll bring that there. So it also needs this offset. So we'd have to supply vector3 int offset. Then this becomes flood fill area helper, node, path data, grid helpers, a step to the north, nodes to process, and flagged for processing. So this should give us a fairly efficient processing of this, in that it will be doing pretty minimal in the way of memory allocations. It's doing what tricks it can to avoid duplicating work and to shortcut things. So that should minimize the amount of time it takes. Now, as I said, it is still a very slow operation, what we're doing. And it is something where there is a lot of data that we're processing. So there is still the potential for this being a little bit of a slow process, but we'll find out once we've got this set up, and we'll just give it another check over before we hit run, because as I said, the potential for an infinite loop with this is quite high, and we want to really avoid that. So that's looking good. We've set up our check with the neighbors. So we're finding the next index. We're checking if it's already been visited in terms of those neighbor flags. We could also check the flag for processing. If it was already flagged for processing, we wouldn't need to look at it, but that shouldn't be necessary. We're checking if there's no connections. That looks good. And then the flood fill, that is dequeuing. So that's looking pretty solid at this point. So now that we've got that set up, let's test and see how this is going and see if we've avoided an infinite loop. So select our path data generator. And what I'm going to do initially, just to limit the amount of stuff we're having to process, is I'm going to switch both of these to be 4x4, so it's a lot less data that it's churning through. So let's tell it to generate the data. So that ran. Let's put in a debug log so we know how many area IDs it built. Debug log, current error ID. That'll give us a good sense of how many it's actually building. So that looks good. And as expected, there's a difference there, which there should be, because this one is able to bridge over to water. So there should actually be a different number of areas. So that's actually good. So that looks about right. One of the things that we potentially want to consider is the size of a particular area. So when it finishes processing an area, we might want to check on its size. So int area size is equal to 0. And so each time we process a particular node, let's update the area size. So plus area size, and that actually might be something I return back. So return area size, and then we're keeping track of that area size. Let's have int min area size is int max value, and int max area size is equal to int min value. Be useful just to know the sizes of areas that we're generating. So min area size is a mathf min area size and a min area size. And then let's do the same thing for max area and max area size. And then we'll just log those out. So debug log min max just so we know what the kind of size ranges we're seeing are. Be useful to see. We don't want to play, we just want to generate. So generate. So there's a bunch of ones that are a size 1, others that are quite large, so that's useful to know as well. And that would be something where what we could do is prune those areas, potentially. So if something's under a certain size, we could remove that as being a valid area. Now we want to check and see how this goes with reducing that size down a bit. Total, just so we know the number of areas. So let's step this size down a little bit. We'll turn this first one to 2 by 2. Just want to see how that goes. We're quadrupling the amount of data. Still generates pretty quickly. You can see quite a large number of areas as expected. Okay, let's switch it to 1 by 1. And this is processing then a lot of data. So we'd expect this to take longer, but we'll see how this goes. We'll generate the path data. So it is processing again 4 times the amount of data, but it still did it pretty quickly given the amount of data that we're processing. And this is the advantage of having that sort of setup where it's avoiding memory allocation to trying to do things as rapidly as it possibly can. But that's something where, okay, we've got some very large areas. There's nearly 5,000 areas in total, so we would definitely be able to look at doing some pruning there of those. But it's working out connected areas. That could be a useful thing to debug. So let's add in, just as a final thing, a debug display with that. So I'm going to put in public bool debug show areas. So show areas, I'm going to make it work a little bit differently in terms of how the debug behaves. So with this, raw areas, f data set debug show areas. Actually do a return because I don't want to draw any of the other ones afterwards. And what I will do, so I'll do this, but the color is going to be based upon that area ID. So gizmos, color, we can do color HSV to RGB. And what we will do is use, actually no, we can do some new color, because one of the color inputs they take the 0 to 1 values. So what we'll do is our node area ID ANDed with FF divided by 255. Then we'll do a similar thing for green and blue. That will handle if we've got a lot of different areas. Or actually, there's a better way we could do that, I think, where if we had a bank of colors, we could actually pick from that bank of colors based upon the area ID. So let's do that, actually. I'm going to have static color area bank is equal to new color. So we can just do color red, color black, blue. Oops. We just want to chuck in as many possible ones as we can. What other ones have we got? We've already got magenta. We won't go for grey. I will chuck in white though. So we'll do that because then our color is area bank, and we use our nodes area ID modulus with area bank dot length. That way then it reuses the different colors, but we'll also do a check for if node area ID is less than 1, then we just return, so we don't draw it. So this should allow us, should mean, it won't guarantee that adjacent areas are a different color, but should mean that there's at least a chance of them being different colors. So we'll turn on that. So we can see we've got a bunch of ones where we have connections not being linked through. And with that, it'd be useful to look instead then at the edges, because the edges do connect. So the edges connect, but it hasn't actually linked up the areas, because we'd expect these to be the same color. And likely this one will illustrate it even more so that we know these are actually connected, because we can see the connections there for them. So that suggests that we have something not quite working with the checks that we're doing here. So we want to make sure that we're building up those area IDs correctly, because that's something that's really important that these work. So we are using the offset there, which is good. We're checking if it's already flagged for processing, which when gets enqueued, we flag it for processing immediately at that point, which is correct. Our index is not being calculated correctly. You can see neighbor index was using the current nodes one. So we're going to need to regenerate that data. So we'll regenerate that. It will take a little bit of time. This may change that processing time. Drastically changes the number of areas, which is good, and in a way that looks really good there. So let's turn on our area IDs now, and that is looking good. That's a lot better in terms of what we expect to see. These are the areas with the water boundaries. So now we have areas where we can really easily tell, is there a connection between them? And we can see, okay, those areas here, that should mean there's a connection we can find down to the ground. And if we follow, there is. Connects down over here. And then these ones we're hitting into steeper areas. So those are getting disconnected, which makes sense. And again, we're hitting into that water area. If we turn this over to this one, probably find very few areas that are not connected. And that is looking excellent. And we'll check our file size because we've made some additions there. File size has increased a little bit, but still very, very manageable. So we've now got our path data working at different resolutions. We've got multiple sets of path data working. We've improved the attributes there so we can have some stuff where it's linking and working with the data differently for different sets, which is great. And we have a mapping of what areas are connected, which is going to allow us some help when we do pathfinding, because we can have two locations on the far side of the map, and to check if there has to be a path between them, we check one number on each of them, and we know if that's the same, a path must exist. If it's different, no path can ever exist for it, so we don't need to do that path find. So it's going to save us a lot of time in the future with that, which is excellent. So next time around, what we're going to be taking a look at is we're going to start building the pathfinding system, because we've got our sets of path data, we've got them nice and robust. They're working well, they're working efficiently in terms of storage, we've got connectivity information, which means we've got the key bits we need to start making some really cool, really fast pathfinding systems. So that's what we'll be taking a look at next time. If you're looking for the code for this project, it is available up on GitHub. As always, fully able to use any of the stuff for this project, the code, the assets I create there, in any of your own projects, whether those are commercial or non-commercial ones. If you've got questions, please chuck in a comment below. Very, very happy to help out. And if you are looking for ways to support the channel, chuck in a like and subscribe. That's something that's very much appreciated. It really does help out. If you're looking for other ways to support the channel, I do have a Patreon, and the link to that's in the description below as well. But until next time, bye.